Hi, today I want to talk about evaluating limits. The question is, we're given a limit, right? We're given something that looks like this, limit as x goes to a of f of x, and we want to know what do we do? What we do to evaluate it? Well, it depends, right? There's always something you should start with, which is to ask if your function is continuous at x equals a, right? If so, then evaluate using continuity. Just plug in x equals a. That should always be your first thing to ask yourself, right? So in that case, the limit would just equal f of a, right? This is the first thing you always want to look for, because it's honestly the easiest, right? It's the best case scenario. So for example, say I had the limit as x approaches a of 1 over x squared, and let's say this a is 3, right? Well, here I would just plug in the 3 because this function is continuous at 3, right? Here's the graph of this function, f of x equals 1 over x squared. There's absolutely nothing strange happening out here at x equals 3, or in this case, the a value, which is 3, right? The height of the function is 1/9, right? That point on the graph is 3, 1/9. And whether you approach from the right or whether you approach from the left, the y values will just converge to the height of the function. So how do you get the height of the function? You plug in the x value and you get the height of the function, right? So this is an example of a continuous function. So you just plug it in, right? This is the best case scenario. And always this should be the first thing you ask yourself when you're handed a limit is, can I evaluate by a continuity? Okay, that is, just plug in the x value, right? Plug in a into your function. So that's kind of your first pass. Now, after that, what if you can't just plug in a value, but maybe you can evaluate it by what I like to call number sense, or say numeric reasoning. This is kind of the second thing you want to look for. So maybe you can't just plug it in, but maybe you can just talk yourself through it, right? In the sense that as x approaches a, sometimes you can just kind of ask yourself, where will f of x go as x approaches a? And you might even try some x values near a, right? Even sort of plug those in for yourself to get a sense for what's happening. So for example, here's a very similar example to the one above. Suppose I had the limit as x approaches 0 of 1 over x squared. Well, here I have the graph, right? So you can see on the graph what it's doing, but say you didn't know that graph. How could you talk yourself through it? Well, what you could do is you could say, all right, as x approaches 0 from the right or from the left, right? It doesn't matter because x is being squared. It will be the same value. What is going to happen? I'm going to have 1 divided by a very small value. Right, so this is not, super formal mathematics, but it's totally valid reasoning, right? So I have 1 divided by some quantity very small. That's very small. For example, if x were, say, 0.1, then 1 over 0.1 squared would be 1 over 0.01, right? Very small number. And like I mentioned before, it doesn't even matter here if it's a left or right-handed limit. You're squaring it, so you actually get the same value whether it's to the left or to the right. This function has even symmetry. So you have 1 over a very small number. Well, what happens if you take 1 over a very small number? Here, I'm saying 1 over 0.01. So this is literally saying how many pennies are in a dollar, right? You're saying $1 divided by 0.01, right, divided by 1 cent. So well, 100, there are 100 pennies in a dollar, right? Well, or you can see it as, you can see it by just sort of reasoning with coins, or you can see it as copied out flip, right? Think of it as 1 over 1/100th if you want to think of it as a fraction, and then you can say, okay, well, that's 100, right? So both of these evaluate to 100. So what is this? This is very large, right? When you take 1 over a very small number, you get a number that's very large. And therefore, we can say that this limit is infinity, because whether you go to the left, from the left or from the right, either way, we're getting a very, very large number from as x approaches 0, right? As opposed to, say I had the limit as x goes to 0 of 1 over sine of x. Say this was my limit, right? So now I could apply very similar reasoning. I could say, okay, say x is 0.1, right? Then what do I have? I have 1 over sine of 0.1, right? And I know by the small angle approximation, I know this is roughly 1 over 0.1, right? When you plug a small number into sine, it returns basically the same value, right? Very, very, very close to the same value. So this would be something like 1 over 0.1. So this is going to be very large, a very large positive number, right? Whereas on the other hand, if I plugged in negative 0.1, then I'm going to get sine of minus 0.1, right? And this is going to be very close to 1 over negative 0.1, which is going to be very large, but negative, right? These are going to be opposite sign. And if you don't want to think of it as small angle approximation, you don't have to. You can also think of it as unit circle, right? Think of the, for small but positive angles, I have a small but positive sign. And for small but negative angles, I have a small but negative sign. Right? So you can think of it that way too. So what do I have here? Well, this does not exist, right? Because the left and right hand limits disagree based on these estimates, these numerical arguments that I made below, right? Because, so when you could say this is the limit as x approaches 0 of 1 over sine from the right is approaching positive infinity, because it's going to be 1 over a small positive number, right? It is positive infinity, and the limit as x goes to 0 from the left is going to be 1 over a small negative number, right? So this is going to be negative infinity. So since the left and right hand limits disagree, the two-sided limit does not exist. Right? So here I'm not being, I'm not attempting to graph the whole function or anything like that. I'm just reasoning by picking some x values near the point of interest, right? So that's why I picked 0.1 and negative 0.1, because I'm trying to analyze what happens as x goes to 0, right? So here the left and right hand limits disagree. Therefore, limit as 1 over sine of x does not exist. Even though I don't really know what that graph looks like, right? So I never graphed it, but I can say that it does not exist. It's not like 1 over x squared where both asymptotes go to the same place, right? Maybe I don't know the whole graph globally, but what I did figure out here with these limits is I figured out that the graph looks something like this. Near 0 has an asymptote this way and an asymptote this way, right? One asymptote to infinity and one to negative infinity. That's what we just saw. So that's another example of this number sense numerical reasoning kind of approach. Here's one more example like that. Suppose I had the limit as x goes to infinity of, say I had e to the minus x plus e to the x. Okay, this is my my limit that I'm trying to calculate. Well, again, I can't really just plug in. I can't do it like case 1 where I just say, it's continuous, just plug in the value. I can't really get away with that because here I have a limit to infinity, right? But I can talk myself through it just like I did these two prior examples, right? I can say, well, as x goes to infinity, what do I have? Here I'm going to have e to a very large negative number, right? This might be most easily thought of as 1 over e to a large number, right? A very large number, plus e to a large number, right? So the negative exponent, you could just kick it to the bottom, right? So you can think of it this way. Well, as I plug in larger and larger numbers to this expression, I have 1 over something massive, right? As I plug in larger x values. And here I have e to something massive, right? Which is going to, again, be massive. So this first quantity, 1 over something massive, that is approaching 0. Whereas this second quantity, e raised to the something massive, that's approaching infinity. So together, these will approach infinity, right? These two, when you add up this, when you do the limit of this sum, e to the minus x plus e to the x, as x goes to infinity, it goes to infinity because the first quantity goes to 0 while the second quantity goes to infinity. So if you add those quantities together, it will still go to infinity. So again, here I didn't do anything really formal. I didn't do any heavy algebra. I didn't even plug in any values, but you can just chat yourself through it, right, with some number sense. And again, if you wanted to do some more specific numerics, you could plug in x equals 10, you could plug in x equals 100 and confirm that yes, that first term is going to 0 while the second term is going to infinity. So that's another example of this sort of number sense numerical reasoning approach. All right, so suppose that doesn't work, right? Suppose you do not, suppose it's not continuous, suppose you can't just plug it in. Suppose you can't just do this sort of number sense numerical reasoning, then you might try to apply some sort of rewriting, like factoring or a conjugate or a substitution, right? So maybe we can sort of clean up the limit with some sort of rewriting. So maybe some factoring, maybe a conjugate. These are very common tricks for cleaning up limits. Maybe a trig identity, maybe applying a trig identity, maybe a substitution, right? There are so many ways that you can try to clean up the limit. And maybe after you clean it up, then maybe you could do one of these easier earlier things, right? After some rewriting, well, then maybe you could just plug in a value, right? After you clean it up a little bit. Maybe after you remove a discontinuity, right? Which is a very specific, very technical term, right? What a removable discontinuity is. Or maybe some, numerical reasoning will apply after we clean it up a little bit. So this is a really common strategy. And here, and these are, this is not a strategy so much as a collection of strategies, right? But let's show a few examples of these. So here is a very, very common setting. Suppose you had the limit, let's say we had the limit of sine of 2x over x, right, as x approaches 0. Well, here I can't just plug it in because I get 0 divided by 0 if I try to do that, right? If I try to plug in. So what could I do instead? Well, let me say, hey, in that numerator, I have a sine of 2x. I have an identity for that, right? Let's apply the sine double angle formula. Right? Maybe that'll clean things up. I don't know. Let's try it, right? There's no harm in trying it. The worst case that happens is we get stuck and try something else. So there's our sine double angle formula. Right. Well, then what I could say next is that this actually puts me in a good position because now I have actually something that's very well behaved at 0, right? 2 times cosine, that's fine. There's nothing weird going on there, times the limit as x approaches 0 of sine x over x. That's our special limit for sine. That's the small angle approximation, right? So I can actually say then, see this limit, this first limit, right? This is back in case 1, right? The continuous, it's continuous, just plug it in, right? So this one, I can just plug in the value, 2 times cosine of 0, right? This second one is a famous formula, right? This is our special limit for sine. This is just 1, right? So at the end of the day, here I get 2 times 1 times 1 is just 2. So that's the limit of this sine of 2x over x, right? This is our sine double angle formula, right? Applied to that numerator, and then you can break it apart into a product of two limits each. Each of those limits exist, so you can split it up, right? So this is one way you could evaluate this using a trig identity, right? But it's not the only way. You can also do a substitution, right? You could say instead, you could substitute. Here's a completely different way to evaluate this. Let's substitute t equals 2x. Well, if t equals 2x, then I have x equals t over 2. And as x goes to 0, t goes to 0 as well, right? So I can rewrite this limit if I want as a limit in terms of t. And why am I doing this? I'm doing this just because I want to clean up what's inside the sine is really the reason I'm doing it, right? So I'm picking this variable t to represent what's inside the sine. So I have sine of t over x. And what is x? X is t over 2. As x goes to 0, t goes to 0, right? And now I can do algebra. Here, I have a 2 that's in a denominator of a denominator. Therefore, it's really in a numerator. And now I have 2 times 1, because again, I hit that special limit for sine. Right, so this is a another way that we could evaluate this. In each case, we were somehow rewriting it to simplify the limit, right? But very different techniques. In this case, I did a trig identity. In this case, I did a substitution. But either way, it resolved sort of strange unknown limit that we couldn't just talk ourselves through, and resolved it in a into just more much more simple, much more manageable case. Right? And notice that both of these cases, I couldn't just talk myself through these with number sense, right? In this sine of 2x over x, if I tried to just say by number sense, okay, as x gets small, the numerator goes to 0, but the denominator also goes to 0. So I have something going to 0 divided by something going to 0. Well, that doesn't tell me anything about what quantity is being approached, right? So that's why we have to do something a little more algebraic, like we did here, either substitution or trig identity. Right, are both great ways to go. All right, so that's our that's two examples of these techniques. Let's look at another. So here is another example, very similar. So let's look at, for example, suppose I had the limit. So I had the limit as x approaches pi, and let's say I have 1 plus cosine x on the bottom, right? And let's say I have x minus pi on top, right? So let's say this is our expression that we're working with. So here again, I can't just plug in pi because I just get 0 over 0, right? I can't just number sense my way through it. I can't just talk through it using some kind of, well, as this number approaches this number, the whole quantity will become, right? Because again, it's 0 over 0, right? Cosine is -1 at pi, right? So I just have basically 0 over 0. So I need some other trick. So this is a great place to try multiplying by the conjugate, right? Because I don't have any better ideas, right? I'm just trying to rewrite it in some other form, and hopefully this other form that we get is more useful than the form we have right now, right? So let's see. So if I do this, let's see what happens. I end up with what? Well, I have x minus pi up top. I have 1 minus cosine x, right? And then on the bottom, I have 1 minus cosine squared x. Right, that's what I end up with. And this is all as x approaches pi. So then what would happen next? Well, next I have, this is again limit as x approaches pi. And then this is x minus pi. This is 1 minus cosine x. And then at the bottom, if I want, I could rewrite this as sine squared of x. Right, so this is a new expression, right? And now I can ask myself where to go from here. Well, if I still can't just plug in pi, right? Because in the numerator, right, I have 0, x minus pi gives me 0 in the numerator. And in the denominator, I have 0 because sine of pi is 0. So sine squared of pi is 0. But what I could do is I could, again, try to do some sort of substitution, right? I could try to clean this up with some sort of substitution to make it look a little more familiar. And in particular, I have this sine squared down there in the bottom, right? So maybe a good thing to do would be to replace x minus pi by something, right? That maybe I could get away from this pi and instead get over to 0, right? If I could replace x minus pi by, say, t, right? So this is combining a conjugate with a substitution. So let's replace x minus pi by t, right? So do t equals x minus pi. Then what do I have? As x goes to pi, t goes to 0, right? If I'm making this substitution, right? And also, if you solve for x, right, you get x is t plus pi. So this gives me something that I can use to rewrite this limit. So I'd have the limit as t goes to 0 of what? I have t up here. I have 1 minus cosine of t, right? Sorry, t plus pi because it's x. So there's t plus pi. And then down here, I have sine squared of t plus pi. Right? So now I can play with this a little more, right? In particular, I could use some angle sum identities, right? I can use the fact that cosine A plus B equals cosine A cosine B, right, minus sine A sine B. That's the cosine angle sum identity. And then I could use also the sine angle sum identity, right? Sine A plus B, which is sine A cosine B plus sine B cosine A, right? So I could use these to unpack that expression. And what would I get? Here I'd have cosine A, which is t, right? Cosine B minus sine A sine B, which is pi. And then on the bottom, right, I have the square of what? I have the square of sine A cosine B plus sine B cosine A. Right. But this looks like a mess, but it's not as bad as it seems because sine of pi is 0. So this goes away and this term goes away, right? Cosine of pi is 1. This should be pi. There we go. Cosine of pi is 1, right? So I can also, sorry, minus 1, right? So I can also plug those in. So I get t 1 minus cosine t times -1. So that's actually going to be a double negative and flip to a positive right? Over what's in the bottom, I have sine squared of t, right? Times cosine of pi is -1. But it got squared, so that actually goes away, right? -1 squared is just +1. So there we go. I've rewritten the limit in this formula. And here I claim we're doing a lot better because even though it might not look like it, we have something a lot more familiar. It helped getting this to sine because now I have t over sine t. I'm going to peel off that factor. And then I have 1 plus cosine t over sine t. This is what I end up with. Right? This I really like because now I still can't just plug in 0, but I can do step 2. I can talk myself through this with some number sets. Specifically, what I can do is I can say, I know what this does. This approaches 1, right? This approaches 1 because t is approaching 0. And sine t and t become equal for really small values of t. This is, again, the special limit for sine, or the sine small angle approximation, right? Now here, I can also talk myself through this limit. As t approaches 0, this quantity approaches 2, right? Because as t approaches 0, cosine of t approaches 1, so I get 1 plus 1 is 2. This quantity, on the other hand, it depends. This, as t approaches 0 from the right, this also becomes a small but positive quantity, right? But as t approaches 0 from the left, then this all becomes a small but negative quantity, right? So this is, the first factor is very stable, right? The t over sine t is just approaching 1. The second factor looks like 2 over a tiny positive number from the right and 2 over a tiny negative number from the left. So this limit will not exist, right? Because this is, right, it's essentially, it's going to infinity from the right and negative infinity from the left. But that would have been hard to see back here, right? When we were way up here at these earlier steps where we had, just division by 0, right? 0 over 0. There wasn't much to do as far as talking yourself through the limit, but you just try rewriting it and hopefully something nice happens. So there's no guarantee that this was going to work, right? You just sort of try it until you see something. So we had this form was 0 over 0, right? So we couldn't talk ourselves through it. So we use the conjugate, right? That's just a good trick in general to rewrite things. It gets things in a different form, right? And we were able to use a trig identity, right? That 1 minus cosine squared is equal to sine squared. This helped us because then we were able to make a substitution. And after we made that substitution, we substituted in for x minus pi, calling that t. After which we were able to use the angle sum identities because now we had t plus pi's inside our cosines and sines. So we were able to use some angle sum identities. And when all of that settled, we were excited because we saw a ratio of a t with a sine t, right? And that lets you, that's good, right? That really helps because that's a special limit that we know. So at least now we had that one factor under control and this other factor, then we were able to talk through with basically this technique 2, right? This sort of numeric reasoning, right? So that's right, a big mix of a whole bunch of techniques to get does not exist, right? That's this limit did not exist. So that's a pretty challenging one, right? Let's look at one more that we can do with this sort of rewriting process. Here's a very classic kind of Calc 1 limit problem. This is the kind of problem that's been, I think, asked in every Calc 1 course that's ever run. So say we have this x goes to say x approaches -1, and I have x to the fourth minus 1 over x squared minus 1. So again, this is 0 over 0, so I can't just talk myself through it with numerical reasoning, right? And I can't just plug in 1 because it's division by 0. So what I can do is I can say, okay, this function, this is discontinuous at -1, right? But I can do what? I can factor, right? This is going to factor, and in fact, I can factor out of both the top and the bottom. I can factor the common factor x plus 1, right? And sorry, x, let's do x cubed minus 1 over x squared minus 1. I don't want the whole denominator to cancel. So x cubed minus 1 over x squared minus 1. So here I have as x with 1. There we go. There we go. That's what I want. Sorry. X approaches 1, x cubed minus 1 over x squared minus 1. That's what I want. So here I can factor the bottom and I can factor the top, right? This is the difference of squares and the difference of cubes formula. And then once I do this, I can cancel this factor right there, right? And when I do that, what do I get? I get something that now I can just plug into, right? So this is back to technique number 1. Right now I could just plug in x equals 1 and I get 3 over 2, right? So this limit is just 3/2. So this comes out actually quite nicely once you factor and cancel. It's worth noting that this is really, we've really changed the function, and here you can really see the discontinuity, and you can see the discontinuity being removed when we canceled it. So I think it's worth noting that if you call this function, say you call this function f of x, so let's call f of x this x cubed minus 1 and x squared minus 1. But if you call this function, let's call this, say, r of x, because we've removed, right? We removed the discontinuity. These functions are almost equal to each other, but they're not quite. There's one point at which they differ, namely x equals 1, right? F is undefined at x equals 1, right? And you can graph this function f using just the guidelines for graphing a rational function from pre-calculus, right? If you want, you could figure out all the features of this graph, right? This is right. This f is, which is this x cubed minus 1 over x squared minus 1. You could do the long division to get the asymptote, right? So you could say this, okay, this goes in x times, and I get x cubed minus x, subtract this off. So I get remainder is x minus 1, right? So this, if you rewrite this function using long division, what do you have? You have x as the quotient, and then you have x minus 1 over x squared minus 1. But that part goes to 0 as x gets large, right? So here's your slant asymptote. Your slant asymptote is always just the quotient, or your asymptote in general is the quotient, whether or not it's a slant asymptote, right? So y equals x is in this case, the slant asymptote, right? And you could graph let's see, what else could we plot here? We could plot the asymptote at -1, right? At x equals -1, this will be undefined, right? We could also plot a few points, right? Say you did x equals 0, right? F of 0 would equal 1, right? So it's the point 0, 1. It's always good to just get yourself a few points just to get some sense of what's going on. You could also test for, well, and let's get a few more. Let's try, how about -2? So what would f of -2 be? It would be, just to get something on that other side, right? F of -2, you'd have -8 minus 1, so you have -9. So let's do f of -2. So you have -9 over negative 2 squared is positive 4 minus 1 is 3. So I'd get negative, I actually get an integer, right? Negative 3. So at negative 2, we'd have 1, 2, negative 3, right? That would be a value there, right? Negative 3, sorry, negative 2 comma negative 3, right? And from here, you could basically graph the function, right? It would look like this, and right, just sort of follow those asymptotes. Once you have a few points and you have the asymptotes, you basically know what the function is doing. Also, you can see there aren't any x-intercepts because x squared plus x plus 1 doesn't have any real roots. You could verify that with quadratic formula if you want. Now, there's only one extra thing here, which is that at x equals 1, f is undefined, right? So technically, this graph has a hole right there. Right, that's the graph of f. There's a hole right there at x equals 1. Right? Now the question is, what on earth is the location of that hole? Well, that hole is a hole at 1, 3 halves. How did I know it was 3 halves? Well, because that's what the limit came out to be, right? It told me, this limit calculation told me that the y coordinates were approaching 3 halves as x was approaching 1. So that's this hole at 1, 3 halves. So this other function r, if I graph this function r of x is the same function, but with the discontinuity removed, right? But with 1, 3 halves filled in, right? So r, if you were going to graph r, you would graph exactly the same function, but you wouldn't put the hole there. You would just draw a nice continuous curve straight across, right? So, so that's why r is actually continuous. So once you reduce that fraction, reduce that rational function by canceling that common factor of x minus 1, it becomes this new function r, that is the same function as f, but you've removed the discontinuity, right? And you get this 3 halves, right, as the actual value at r and not just the limit, right? For f, the limit is 3 halves. For r, the limit is 3 halves, but it's also just the value. So that's yet another trick for evaluating limits, is this factor and cancel trick, right? This is a very, very common thing that you look for when you're trying to evaluate a limit that you can't get one of these earlier ways, right? We have, once again, we have just plug it in, it's continuous. We have number sense, numerical reasoning, right? We have can you clean it up with factoring, a conjugate, trig identity, substitution, right? So the previous examples we saw conjugate being used, 1 plus cosine to 1 minus cosine. We saw trig identities being used, angle sum identities, double angle identities, right? If appropriate. We saw substitutions being used. Here is one where factoring ended up being the trick, right? It was a rational function, polynomial or polynomial. Well, you can rewrite polynomials, you can factor them. Maybe there's a common factor that cancels out, right? That's what we had here. We had that common factor of x minus 1 that canceled out, and we were able to then exploit that, right, to remove the discontinuity. So, all right, so those are 3 nice ways to evaluate limits. The last way that is very common in calculus to evaluate limits is maybe if all of the above fails, maybe you could do a sandwich theorem, right? Maybe the sandwich theorem can tell you something about what the limit does. And this, I think a great example of this would actually be to revisit this one that we had right here. But say if you wanted to know what does that do as x goes to infinity instead of as x goes to 0. So let's look at sandwich theorem. So this would be, what is a sandwich theorem argument? Sandwich theorem is the technique where you say, all right, I want to look at some limit, but it's sort of a strange quantity, right? I have sine of 2x over x as x goes to infinity. So the trick is I want to bound this between 2 other functions. I want to say, hey, you know what? Sine of 2x, this is always between 1 minus 1 because it's sine of something, right? I can then, as x goes to positive infinity, I could divide this inequality by x. Right. And I don't have to worry about flipping the inequality or anything like that of dividing by negatives because x is going to positive infinity. Certainly x here is positive, right? So divide by x. So I'm starting out with just the range of sine. Sine is always between 1 and -1. Then I divide by x on all three of these pieces. And now I could say what? Well, what's the limit of the lower bound? That's 0 because it's -1 over infinity, right? The limit of the upper bound is also 0 because it's 1 over an arbitrarily large number. So the upper and lower bounds are going to 0. Therefore, the quantity in the middle must also go to 0. Because it's trapped between two quantities that are both approaching the same number, namely 0, right? So the graph would look like this. We have up above, I have the graph of the quantity 1 over x. Below, I have the quantity -1 over x, right? And these are both approaching a limit of 0. So in between, I have this quantity sine of 2x over x, which does oscillate, but it's oscillating with an amplitude that's bounded by 1 over x and -1 over x, right? So it's, well, the amplitude is bounded just by 1 over x, right? But the max and min values of this function in the middle is those they just bounce between 1 over x and -1 over x. Therefore, the function in the middle also goes to 0 as the limit goes to infinity. So the sandwich theorem is, maybe the most limited in scope, but it's a great tool. Sometimes, if you can argue that your function is, that your messy, hard to understand function is between two cleaner functions that are both approaching the same value, then it's very effective. All right, so those are, for me personally, at least, sort of the four big ways of approaching limits. The sort of the basic. There are other more advanced techniques, right? But the four sort of Calc 1 techniques, and those for me personally that's the order I apply them in, right? You can have different workflow. This, the order that you apply them in is not anything objective or universal, but this is, I think, the best workflow. So, all right, great. Thanks, and hope that was helpful. Limits.